Hello. Hello. Yeah. Okay, now it's working.
Okay. So should I restart or keep going from this point?
It's always
Okay. Yes, it seems. So as I say, this phase is quite short, about 0.1 and up to 1 second. It not depends on what is the final outcome of the supernova. There is a neutron star or a black hole or whatever. This phase of emission gravitational wave is more or less always happening. And this time, the proto-neutron star is accreting mass from the iron core and is growing from up, starting with 0. Solar masses and maybe 1.4 and 2 solar masses, depending on the cases. And it's also collapsing and cooling down, so it will shrink. The radius will shrink from 30 kilometers up to 10 kilometers. The thing here is the scenario at the very beginning is very, very different. It's much different from the last. I mean, we start with something which is about 30 kilometers and 0. Solar masses, and we will end with an object that has 10 kilometers and up to 2 solar masses. So the scenario changes very, very fast during this period. And the main emission, as I said, it was in this part. We have the proto-neutron star. We will the source of our emission will be like the bell, as this is coming from Pablo Cerdà's typical this plot. And this bell, this proto-neutron star, is hit by some instabilities as is accreting mass, and like the convention or the SASI I mentioned before, that we produce excitations of these normal modes of oscillation of the proto-neutron star that will correspond to the gravitational wave emission produced by this scenario. This is the typical gravitational wave signal from this kind of the quorum-core supernovae. The main characteristic of it is highly stochastic because the perturbations and that produce the gravitational wave are essentially stochastic, so the emission is also like this. So it's not possible to have a dense bank of templates that to do parameter estimation with that. So this is one of the main reasons. But if we look at the time frequency evolution of this kind of modes, of this kind of emission, you will see that for all the groups, all the codes, all the progenitors, you have these increasing arcs in frequency that corresponds, and that I will prove later, to one of the normal modes of oscillation of proto-neutron star. So we cannot check instantaneously the gravitational wave emission because it will be stochastic, but the time evolution, the time frequency evolution is more or less clear and well known in all the simulations. Of course, there will be in all the simulations will be other features like this mode here or this one here that will be produced for other different sources of excitation of the proto-neutron star. This is commonly this low frequency thing around 10 Hertz, 100 Hertz is mostly known to be produced by the SASI, and other kind of mode that like this that goes low in frequency, and this one will appear or not depending on the scenario. But it's unclear now when these kind of features will appear or not. Something is under study. Our goal with this project is to make a parameter estimation with core signals. It is the end of this. However, as I mentioned, this waveform is highly stochastic. The simulations takes like a month in a supercomputer to get just one progenitor, so it's not possible to have a dense bank of templates to compare with the signal. So our idea is, okay, let's analyze the gravitational wave emission, taking the time frequency and the spectrum, and see if we can analyze the perturbation of the proto-neutron star, the modes of oscillation. If we can relate with the gravitational wave emission, we have a way to study different simulations, even 1D, you cannot compute the gravitational wave emission because there is no way to do that, and have more and more information to try to relate the emission with the parameters, with the physical parameters of the proto-neutron. To do that, we developed the perturbation equations in general relativity, But to simplify the case, we use 1D equations. So from a multidimensional simulation, 2D, 3D, or whatever, we take 1D angular average, we solve the eigenvalue problem, which is the way we this like the normal oscillation is an eigenvalue problem. So essentially what we take is for each time step of the simulation, we compute the equation, we solve the equation, we have a set of eigenvalues and eigenfrequencies for each of these things. And at the end, we can put them together and produce this kind of plot, which we will compare with the spectrum of the gravitational waves. So the first step is try to relate this modes emission with the gravitational wave emission and see if there is a correspondence between them. This problem is not completely new. It was many works working with that since Reisneger and Goldrich in the 90s. But they use simplified background to compute the equation, something that is with TOB or some polynomials that fit the emission. And our contribution, what we change with our code is to use the background from a real numerical simulation. We have the outcome of a simulation, we read the results, we compute the eigenfrequencies of the most normal population, and we also get this is another approach from the 5-6 years ago. We also include general relativity in the formalism, so we can compute perturbation of some of the labs on the conformal factor. And we also use a global treatment with the whole scenario. We compute also the proto-neutron star and the surrounding up to the shock. And we have this code, it's called GRADE, General Relativistic Model Analysis Tool, which is public and can be used to analyze any kind of calculus simulation. We provide all the tools that if you have a simulation, you want to extract the different modes, you can download the code, adapt to read your data and compute the
Can you say this again? What do you mean by background simulations?
I mean, I want to solve the equation, but the equation is based in different quantities, density, pressure, mass, whatever. To compute the solution, you need these quantities. This at the beginning was just simplified, taken from something simplified things, pseudo-analytical. What we do is, okay, read the simulation, get the output from the simulation, how these quantities evolve with time, and we read it and compute the equation for this more realistic scenario. This is essentially we have a program, we make a perturbation analysis and we see how these quantities evolve. So as this is the emission from a given simulation, we compute the nodes and you see there is a remarkable similarity between the evolution of the different modes with the gravitational wave emission. Not all the modes will produce gravitational waves, only a few of them. Knowing which of them will produce gravitational waves is an open issue. It's not clear when it will appear or when not. But at least these three modes I'm showing here, I will explain the later. You see that this main arc corresponds to this yellow line, and this goes down in blue. You have some chances to see that. Essentially, what our conclusion is, the normal modes of oscillation are the main source of the gravitational wave emission. This is the idea. As I mentioned, there are different open issues, which is the dominant mode, and also keeping the idea that we want to make parameter estimation, how these modes are related with the proto-neutron star. So let me stop a bit about what are the different modes and what are the nature and how we try to distinguish between them. When you have just a radial oscillation with a non-rotating stars, if you are analyzing the fluid perturbation, you only have P mode. With the restoring force or pressure, they are produced by standing some waves, and they are related with something called the Lang frequency, which is something related with the speed of sound inside the scenario. And also, they will evolve. The frequency of the mode will evolve with this with the change of the speed of sound, essentially, which is depend to the main density of the system. Here. However, when you have non-radial oscillations, which is what we want to analyze because it's the source of gravitational wave, we found, or you can find two different kind of modes. Something called F mode, the fundamental mode, that only appears when the L is larger than 2. This is supposed to be the fundamental because it has no node, any cross by 0 inside the star. And if you go to bibliography, you will see that this is also called the lowest P mode, the lowest frequency P mode. But it's not clear which is the F mode. In some simplified scenarios, it's clear, but not, I will show you that in this case, it's not completely clear which is the fundamental. And it's also due to, as it's essentially a P mode, it depends on frequency with the same as the other P mode, so it's with the lambda frequency. Additionally, we have another family, big family of modes, which are the G modes or gravity modes, with the restoring force is buoyancy. And they are related with the Brun-Weisel, which you see here, which is the gradient of the gravity term, and also some terms, some derivative of the pressure and the density, which are related with the entropy and the composition of the fluid inside the shock. And the frequency dependence is different and essentially are related with the whole with the surface gravity, essentially of the system. We will see that this a bit with detail. Analyzing the modes is not an easy task. When you have a very simplified system, essentially you can distinguish. You plot the frequency, the Brun-Weisel and the Lamb frequency. What we see is the dependence with the different modes, and we put the radius. You see with the frequency you can identify the different regions. The first region is the acoustic wave. It's called the acoustic wave region, where the acoustic wave can propagate. Then we have another region, which is the gravity wave region, which again, similarly to the other part, is where gravity wave can propagate, and two different regions that essentially the wave cannot, any wave can propagate or will be go to zero exponentially very fast. So we can identify clearly three different regions. So you compute the different eigenfrequencies, eigenvalues, and you will see different frequencies will be the eigenvalue, the shape of the mode will be the eigenfunction, and we can distinguish essentially the three I mentioned before. We have P modes in the acoustic wave region, where the F mode is the lowest frequency P mode, essentially with no crosses by 0, no nodes. And when we increase frequency, we have the different P modes with 1 node, 2 nodes, or whatever. However, the G modes works in the other way. They increase the number of nodes when the frequency decreases. So the F mode looks like an symmetry plane when we have increasing frequency for P modes and decreasing frequency for G modes. Okay, this is a bit makes the things a bit complicated because the first G mode will be the closer to the F mode, the second one, and so on. However, also with simplified scenarios, these kind of regions are not well defined. So you can have something which couples from different frequencies. You have G modes and P modes at the same time. So they will couple somehow, which is not completely clear. And the things become more and more complicated. And the main feature here is you can have a F mode, in other words, the low frequency P mode, but is coupled with some G mode on the same frequency. So it will stop having, the idea is the F mode can have nodes. It's not defined as the other case. So the things are a bit more complicated. And it's even worse when you compute the different regions for a real simulation, when the thing is completely mixed up. You have a clear region with high frequency, which is acoustic wave region. Some frequency below all the modes will be G modes, and something in between where you have coupling between G modes and P modes in a non-linear way. So it's difficult to find what is happening here and what is the F mode. So this, I mean, the thing is, I haven't mentioned, but the idea to have parameter estimation, we need to trace the different modes. Each mode, each point I show you in the spectrogram of the modes is independent from each other. So we need to to have a correspondence with the evolution of the proto-neutron star, we need to trace them in time and frequency and say, okay, this point is related with this other point and make a fit. And we have to do that. However, as I mentioned before, they have twin couplings, and these couplings appear in the form of the avoided crossings. There are very simplified scenarios here. We have a background which is parameterized with one parameter. We can change and see how the modes, the frequency of the mode are changing slowly with this parameter. And we saw this kind of things. For instance, we have a P mode here that goes down some frequency in green, and at some point it becomes black. It's like the frequency of the two modes here try to avoid to cross. This is why it's called avoided crossing. And also here in this plot, you see the same. You have the plot here, which is evolving in frequency like this. At some point, the frequency changes just to avoid to cross to another mode. And these things are related to how the different modes are coupling to each other. If there is no interaction between them, they are not coupled at all, they'll cross. You trace one mode and the other, and they cross completely. However, when you start to have some kind of interaction between them, if this interaction is weak, you have this kind of avoidance crossing. With this, the frequency of the modes that change, and they don't cross. But if the interaction is strong, you have something which is not like this. You have like a non-linear coupling everything. It's not possible to trace with the different modes go. However, with the avoided crossing, we have this kind of things. This P mode should be like this, and this other mode looks like this. So the avoided crossing is an artifact of the coupling. It's not the true evolution of the modes. So the problem we have now is, I will show you, is that how to avoid this avoided crossing, how to trace or follow the modes when you have this kind of changes in frequency. And it happens many, many times, as I showed you. This is a spectrum of modes, a 2D simulation from a 20 solar masses model. And essentially, the first way to try to classify the modes and try to trace them in time is to just count the number of modes, the number of crosses by zero by the H-Epsilon function. And when we do that, you see this kind of spectrum. For instance, you have here some modes in yellow. At some point, you are going to cross for these dots here in green, and essentially we have the avoided crossing. It just goes down and the other go up, and they don't cross. And also there are problems because the F mode, defined as I mentioned before with the zero node, appears at the end, but when you go backwards in time, it essentially disappears. There is no any mode with zero nodes. So this kind of classification is very easy, but has many problems. But is, I mean, by other authors like Sotani and Morozov, essentially two groups that are working in this kind of analysis, they use this kind of classification because it's the easy one. I mean, you don't have to do any special thing. You just get your functions, compute the number of crosses by zero, put the numbers there, and you see like you have a trace, a classification of the modes. Everything goes. I mean, you can see, okay, give me the red one, you will get, okay, there is the one with 2 nodes, and I will do, and you will have the evolution. This is what they get. But you can see here, but they have also this avoided crossing. When the F mode goes down and it starts to cross with the G1, the frequencies go up and down and they never cross. Even if you see that the F mode should go like this for the whole time. This has this kind of problems. Also in the work with Morozov in 2018, they have the same. You have the zero node, the fundamental node, that essentially at some point it disappears. It starts to cross to other kind of modes, and the zero node disappears. So this kind of classification has the advantage. It's very easy to compute, but it has some problems when you want to trace the modes in a more precise way. To prove that, what we try, to prove that this method is essentially wrong, we do this kind of analysis. We can take the energy of each mode. I mean, it's a combination of the eigenfunctions we have, and trace backward in time like a spectrogram on this kind of colors here. So starting, for example, for the green one, we have this kind of spectrum. When you see, I don't see if you can see clearly, but this line in black is the surface of the proto-neutron star. So this is the interior, and this is the the region up to the shock of the shock of the corpus. And you see you have, in this case, you start with something which has two nodes outside, with some 0, and some point when it arrives to this cross, all the energy is inside the proto-neutron star. If you do the same with the other mode in yellow, you have essentially something which is inside the proto-neutron star, the energy is inside, and at some point, it appears to be outside the neutron star. So it's clear that we have interchanged this, the nature of this mode. This mode at some point appears here, and this energy appears here at some point. So it's clear we are mixing things. We also try another classification with a modification of the number of nodes when you can compute the nodes in different regions, and you have this kind of specification. Essentially, the F mode always appears. You have always something which has a combination of both, can be labeled as a fundamental node, but has the same problem with avoided crossings. I mean, you are tracing bad when the modes goes close to each other. So in our paper in 2019, we try to fix this with this called matching classification. Essentially, what it does is for each point, we compute the eigenfunction, starting, for instance, at the end when everything is more clear. For this point, we take a point, we get the eigenfunctions, we look for the eigenfunctions or all the modes in the previous time and try to find where the eigenfunctions are similar, more similar to each other. So we are tracing backwards in time every point to try to follow and avoid. I mean, and you see here with this method, all the crossings are well defined. They are not points going to interchanging things. I have more proof about this matching is the correct one and not the other. I'll show you in a few slides. The problem here is how to label the nodes, the modes. Okay. What is now with this, which is F mode, which are P modes, what are G modes, is more complicated. In other way, you have a 0, you say, okay, if you are increasing number of nodes, will be P modes, and you are decreasing number of nodes, it will be G modes. You have a clear symmetry plane to make the labels. But here is not completely clear. You have to put labels by hand. And the bad thing about this is it has to be done by hand because there are many parameters you have to change to have the correct results. And it takes like 10 to half an hour to have good results. So if you want to analyze 1,000 simulations, you cannot use that time. So we are trying to find an automatic way to make this classification. And essentially, when you get the energy, you see that in this case, you have everything is continuous. So up to some point where here everything is mixed up because the system is much complex and it's not so clear. It's not so easy to get. But essentially, up to 200 milliseconds, you have a clear mix. But of course, there is coupling between them. You cannot avoid the coupling. But essentially, this matching method is working. The other open issue in the community, I mean, the community is reduced because there are only 3 groups, but there are some issues, is where to put the boundary conditions. As there is an eigenvalue problem, you have to fix the boundary condition at the center and at the border. You can do essentially in two ways. What we do is to impose the boundary condition at the shock point, which is well defined. And I mean, it's a sonic point, is where the fluid changes to fall supersonically to subsonically. So there is a very clear point. And it's easy to impose. We just impose that one of the eigenfunctions cannot propagate outside there. So this will be a node at this point. And we cannot propagate outside because the density is much higher. The other way is to impose the boundary condition of the proto-neutron star. As the proto-neutron star will be the main source of gravitational wave, you don't want to take care about the other part of the shock, and you put boundary conditions there. The thing is, the surface is not very well defined. There is not a clear point defined where the surface of the projectile is. At the beginning, you have something which has, I don't know, 1 kilometer, 2 kilometers, and it's shrinking and getting narrower, but it's not clear at that point when you have the surface. So your results will depend on where you put this threshold in density to define the proto-neutron star surface. So here there are two different things. And also when you do this, essentially you will lose all the modes that belongs to the shock region. But it's not essentially bad because I will show you later. Okay, this is what I was saying. When you put the proto-neutron stars, you will see different things. But in this case, when you use the shock, you will see that there is different families of G modes. It's not so easy. It's making more complicated. You have essentially you will thought that you have P modes and G modes. But when you make a bit deeper analysis, you will see that you will have different families of G modes produced by the buoyancy, but with different behavior in frequency. Essentially, what we have is something that goes like this, increasing in frequency, like the arcs, but you see here in green, there is a mode that goes essentially down with time in frequency. So the nature of this mode will be different from the others, even if there is a G mode. So the things becomes a bit more complicated. So to take into account this, what we do, this is our more recent change on the code, we modify the code to put boundary conditions wherever you want. And principle was fixed to the shock position, and now you can put a threshold in density and try to impose different things in different processes. You can compare essentially the same simulation, put in the boundary condition at the shock and put the boundary condition on the surface. And you see, in the case of surface, this thing on the right is more clearly, there are less modes here. But if we compare both, you can see that some of them are very, very similar shapes, same frequency, time frequency distribution. So some of them, the most shown here at the shock position, should belong only to the surface of proto-neutron stars. And all the points here that oscillate a lot, this blue and green spots, they are not shown here. There are most that belongs to the shock region. So we are more or less, and you see here that I will compare there. You can compare those putting overlapping the other. It's not very clear, but there are points and crosses. And you see here that this point, this mode here and this mode here are essentially the same in both kind of calculations. So essentially they are the same. And the other dots here are only due to the shock region. I want to mention this one in yellow here, which is just crossing all the modes from when you put the boundary condition at the shock, and you see essentially the explanation here is this is a P mode from the interior, which is coupled with the P modes of the outside region of the proto-neutron. So the things mix in a non-linear way, very complex. But you have an interaction between them. But these modes are clearly well defined. Here is the same, but what I do is put as a black dot the coincident points between both calculations. So you see here, like this mode and this mode and this other G modes corresponds to the proto-neutron star. And if we compare this with the previous, taking this into account, this mode will cross all the other modes, also this one. They are not changing, but here you see that the overmatching is tracing correctly this kind of nature of the mode. So our matching method is much better than the other one because it's taking this into account. The other key thing is the open issue is the level of the modes. The thing is, this strong feature of the spectrum that belongs to what mode? The G mode, the F mode, what is this? And more or less, the thing is, we know with our method, we cannot put labels at that easy way. So we know that this is a G mode because corresponds to the surface, it traces with the corresponding frequency. But when you have, for instance, Sotani calls the G mode just the one with this strong emission, and we call F mode the first of the lower frequency P mode. depending on the simulation of what definition you use. But essentially, it's just a label problem. I mean, if you are interested in these things and you read the papers, you will see that we call different things, but they're essentially the same. It's a label problem. It's not a physical problem. It's the way we put names to these things. But essentially, all of the groups agrees that this mode will be the most important for the gravitational definition.
That thing that you call F mode, independently of which refers to that thing as an F mode, has a unique physical.
I mean, but the thing F mode is a labeling thing. If you call, like the bibliography says, that is the lower frequency P mode, this is the mode I show you, which is more or less around 200 and this like frequency in blue. If you call just the first, then with 0 nodes, and then you have P modes and G modes, it's this one that goes up to 500 kilohertz, 500 hertz.
But is that a pure discrepancy on what I name F mode,
yes,
or on what does represent a given physics?
No, it's just a label name essentially. The thing is, the difference is if you say F mode, you are saying that this is a P mode, because by definition, fundamental mode is a P mode. In our case, we know that this is a G mode. Well, the reason I'm showing here, because it corresponds to the Brown-Weisala frequency. This is from the interior, and it doesn't goes to the. I mean, we can compute. We can compute only P modes and only G modes, making some approximation. And when we compare only P modes, that mode doesn't appear. You have a similar shape in this thing. So we know it happens when you make the G mode approximation. And also, if you compute here the Brown-Weisala frequency and the mode, you see that the dots in white, the region in white are where the Brown-Weisala is bigger, and you see that corresponds to the interior of the proto-neutron star. So corresponds the evolution corresponds to the Brown-Weisala. So we are, I don't know, 100%, but we are very sure that this mode is a G mode and not a P mode.
But these modes are not dependent on like a mass or density. So
I will go to that in a moment. These are the answer to your question. So once we agree that we have a method to classify the modes and trace them in frequency, the next step is to try to relate this frequency evolution with the evolution of the properties of the proto-neutron star. So what we do is we compute, like as I mentioned, it's very complicated to trace them. It takes a lot of time. So we cannot compute as much simulation as we want. So we take a set of 25 1D simulations. You use two different codes. I use Alka from Martin Gowling and Coconut by Harry Dimmenmeyer. We use 6 different equations of state, hot equations of state, and we vary the mass of the proto-neutron. We have 8 proto-neutrons between 11.2 to 75 solar masses. And what we do is try to relate. We get we trace the different modes, P modes, F mode, all of them, and try to make a fit between different quantities of the proto-neutron star. And what we get is this. They are quasi-universal because it doesn't depend on the code, it doesn't depend on the progenitor mass, it doesn't depend on the equation of state. We have similar behavior in frequency. So essentially what we do is that the F mode and the P modes fits quite good with this quantity, which is the square root of the mass of the radius to the third, which is the main density inside the shock. You have this is just a polynomial fit. I mean, there are differences because codes are very different, the neutrino treatment is different, and the gravity treatment is different. So we can get something, but if you make the same analysis, you get something that goes straight line with the different codes. And we do the same with the G modes. But essentially, they scale with the surface density, surface mass of the surface gravity of the proto-neutron star, as I mentioned at the beginning, with the different scales. And there is a third degree polynomial, and we got these fits. This, I mean, our fits are 1D. They have some problems according to 1D. But we compare with the results that get from Sotani in 2021. Their fit and our fit more or less agrees with some error bar. Even if they use 2D simulations to perform their analysis. And also, we also compare with the gravitational wave emission computed by Powell and Mueller. There are 3D models, and you see that this is not the modes, they are the fits. I mean, you compute the evolution of the mass of the star and the radius, apply our fits, and you get this white line that up to some error, it fits correctly the gravitational wave emission. So more or less, we know that the gravitational wave emission can be related with the evolution of this parameter. And this is we have worked on. We have a work with that. Essentially, what we get is this is the inverse problem, the inference. When we get the inference, what we get from here is not mass and spin or something like the compact binary coalescence. What we get is a trace of the evolution of the parameters of the proto-neutron star, essentially mass and radius with time. Okay. So the idea is we will have the gravitational observation from the LIGO Virgo detectors. We will apply our relations to get from the frequency of the gravitational emission the time evolution of the mass and the radius. And we have some work, we have one paper on that, and we are working in the real data with ET detectors and so on. But it will be another different. But essentially, we are able to do that. We can trace with some error bar. Now we can obtain the emission of the evolution of the physical parameters of the proto-neutron stars using the fundamental relation we have derived with the analysis of the proto-neutron star normal modes of oscillation.
So you use both like F and G mode, or is just?
I mean, we assume that this is the G mode, well, we call G2, but we know we have the fit, which is this one. We have a polynomial relation between the frequency and the evolution of mass and radius, so we can apply an inverse problem. Right? We get the frequency from the emission, from the gravitational wave theta. We use the relations to make the inverse relation, and we will get the time evolution of the mass over radius.
Assuming you have the right equations.
No, because it's independent of the equation of state. So it depends on the equation of state, but not strongly. I mean, you will have something. The thing is, the error bars here are quite big now, because we only have 25 simulations. There is not in the community a code, or every group has different codes with different things. They are not essentially the same. From some years ago, they start to converge to get the same results with different groups, different codes. If you put the same physics, but they're not agree completely. Means for some groups you have a progenitor that explodes, and if you use a different code, it doesn't explode. So the thing is, the state of the art of simulations are far away from giving a very clear things, because when you advance in computing and you advance in the physics inside, the codes will evolve, and you have a lot of uncertainties, and these uncertainties appears here in the error bars. So if there is independent with the equation of state, we cannot see that now, because we have too many errors. It's quite complicated. And just to finish my talk, we are taking some steps to understanding an emission mechanism for supernova and the proto-neutron star with this goal. We have many open issues with the classification, where to put boundary conditions, what is the nature of the other modes, also the fundamental one and the others that go down, that appears. I don't remember you see at the beginning of some simulation I showed you, there are some traces that this mode that go down. So some points it is excited and will produce gravitational wave, but it's not clear how this mode works. And for the future work, we want to extend our equations to take into account rotating stars, but we have to go to 2D equations, and the number of terms in the equation will go from, now it's around 6, will be 1, 25 or something like this will be much complicated to compute. And we are also checking the boundary conditions to take into account the advection mechanism to have a clear relation between the P modes and the standing equations of stability. That's something is already done by one of our students, and we will publish the equations at some point in the near future. So that's all. Thank you.